Hello, this is George Benbow and welcome to the derivation of Rutherford's scattering equation. Before we start, we have to make some assumptions to make our lives much easier. The charge of a particle being projected is Z1e and the charge of a nucleus is Z2e. The laws of Newtonian mechanics still apply, and this is purely based on electromagnetic forces. Gravitational forces such as gmm over r squared need not be considered. The nucleus and the alpha particle are treated as point-load particles with point charges at their centres. And finally, each particle being projected is only deflected up to once by a single nuclear charge, hence why it is extremely important to use a thin gold foil in the experiment. We start off with our angular momentum L equal to mv0b, but using L equals the cross product of the momentum and r, we get that L is also equal to mr squared divided by dt. When we make these equal to each other, we can eliminate m on both sides and make r squared divided by dt equals v0b, and this is going to be our first equation. Now let's move on to regular momentum. The magnitude of a momentum before, pi, is equal to the magnitude of a momentum after, pf, and we shall call this value p. The magnitude of the change of a vector shall be called delta p, and we can visualise these using the parallelogram rule. If we bisect the parallelogram along its longest diagonal, we see that it is perpendicular to the shortest diagonal, delta p. Remembering that the angle inside the triangle corresponds to the deflection angle, theta, we can see that each of the bisected internal angles is theta over 2. Using some simple trigonometry, sine theta over 2 is equal to 1/2 delta p over p, which is equal to delta p over 2p. Rearranging this, we get that 2p sine theta over 2 equals delta p, which we should call equation 2. Newton's second law states that F equals delta p over delta t, and we can imply from this that delta vector p equals the integral of vector f with respect to t. This implies that delta p equals the integral of f cos phi with respect to t. The equation for the electromagnetic force between two charged particles is equal to their charges over 4 pi epsilon naught r squared. When we substitute this back into our original equation for delta p, we get that it is equal to the integral of z1e, z2e, cos phi all over 4 pi epsilon naught r squared with respect to t. Every component in the force apart from r remains constant, so we can take these out of the integral, and with some rearranging inside the integral, we get that delta p is equal to z1, z2, e squared over 4 pi epsilon naught, multiplied by the integral of dt over dr squared, multiplied by cos phi. You'll see why it's important to place dt where it is in a bit. Rearranging equation 1, we see that dt over r squared is equal to dphi over v0b. Substituting this into our equation for delta p, we get z1, z2 e squared over 4 pi epsilon naught multiplied by the integral of dphi cos phi over v0b. Rearranging the quantities inside the integral, we get 1 over v0b cos phi with respect to phi with currently undefined limits. In order to define these limits, we use the fact that the sum of the limits plus the deflection angle is equal to pi, and the upper limit is equal to the negative of the lower limit. From this, we get that the limits are plus or minus pi minus theta over 2. Substituting this back into our original integral and integrating, we get z1, z2 e squared over 4 pi epsilon naught v0b multiplied by sine phi with the limits, and this is equal to z1, z2 e squared over 4 pi epsilon naught v0b multiplied by 2 sine half minus pi, and using the suitable compound angle formula, the trigonometric function simplifies to cosine theta by 2. We now have two different expressions for delta p, so we can set them equal to each other and rearrange for b. We get that b is equal to z1 z2 e squared over 4 pi epsilon naught pv0 tan theta over 2. Neatening this up, we get to b equals z1 z2 e squared cot theta by 2 all over 8 pi epsilon naught times the initial kinetic energy of the particle. This is equation 3. Using the fact that the kinetic energy is equal to the force divided by d0, the distance of closest approach, we can make d0 the subject and make the value of b much more compact. b equals d0 over 2 cot theta by 2 is not necessary for the calculations, but it makes them much more compact. Now let's talk about flux. Flux, F, is the number of incident particles arriving per unit area per second at a given target. The number of incident particles with impact parameters between b and b plus db is equal to the flux multiplied by the area between concentric circles of radius b and b plus db respectively. The number of incident particles, dn of b, is equal to f pi times b plus db squared minus b squared. This simplifies to f pi 2b db plus db squared. Since db squared approaches 0, it is considered negligible, and dn of b is expressed as f pi b db. d by d theta of d0 over 2 cot theta over 2 is equal to d0 over 2 times minus a half cosec squared theta over 2, which equals minus d0 over 4 sine squared theta over 2. d by d theta of b is simply db by d theta, which is minus d0 over 4 sine squared theta by 2. Consequently, db equals minus d0 over 4 sine squared theta over 2 d theta. We can now write an expression for the number of incident particles in terms of theta instead of b. dn of theta equals f2 pi d0 over 2 cot theta over 2 times minus d0 4 sine squared theta over 2 d theta. This simplifies down to f pi d0 squared over 4 times cot theta by 2 over sine cubed theta by 2. dn of theta equals f times the differential cross section d sigma. Therefore, dn of theta over f d theta equals d sigma by d theta, which equals pi d0 squared over 4 times cosine theta over 2 divided by sine cubed theta over 2. Typically, the differential cross-section is denoted in terms of a solid angle, omega, which comprises of a scattering angle, theta, and the azimuthal angle, phi. The omega is equal to sine theta d theta d phi. Using the double angle formula for sine 2x, this is equal to 2 sine theta by 2 cosine theta by 2 d theta d phi. d sigma by d theta is equal to d by d theta by d phi multiplied by the range of phi, so it is equal to 2 pi d2 sigma by d theta d phi. We can rearrange it to find that d2 sigma by d theta d phi is equal to 1 over 2 pi multiplied by d sigma by d theta, which is equal to d0 squared over 8 multiplied by cos theta by 2 over sine cubed theta by 2. Finally, we can write that d sigma by d omega equals d0 squared over 8 multiplied by cos theta by 2 over sine cubed theta by 2 multiplied by 1 over sine theta by 2 cos theta by 2. The cos functions cancel out, so we are left with d0 squared over 16 sine to the 4 theta by 2. When we expand d0 squared and simplify, we get that d sigma by d omega is equal to z1 z2 e squared over 8 pi epsilon naught ek all squared times cosec to the 4 theta by 2. And we are done. Finished. Finito. QED. We have derived Rutherford's scattering equation. Thank you very much for listening.